Hello friends, welcome back. Today we will be learning about complex numbers. So what exactly is a complex number? Now a complex number is the standard notation of representing a complex number is this. Let Z be the complex number. Now the complex number is actually a superset of real numbers and imaginary numbers. So I can represent this as A plus IB, where A is my real number and the real part and B is my imaginary part. Now what exactly is I? I is the square root of -1, and this is what, now since we know that the square root of a positive of a negative number does not exist, that is why I is called the imaginary part, and hence the coefficient of I is the imaginary part of the complex number, right? So how exactly can we geometrically represent a complex number? This is the way now. Let x represent the real part and let y represent the imaginary part. Right? Suppose my A is somewhere here and similarly say my B is here. Right? So this line represents my complex number Z for some specific value A and B. Right? Now we know that since this angle is 90 degree, now we define the modulus of the complex number Z, and the modulus is represented as mod Z is equal to square root of the sum of the squares of real and imaginary part. Similarly, this angle theta is called the argument of the complex number Z, and the argument written as arg or just theta is tan inverse of b by a. Fine. Okay. Now again, as we studied in the lecture series of trigonometry, we know that theta should lie between minus pi by 2 and pi by 2. Right? I'll write it in different form. Okay. The endpoints are actually included. Right. Okay. So now let's go to how we can represent a complex number in a polar form. Okay. So this is how I write it. This is called the polar form. Why polar? Because we have written it as in terms of some angle and some radius, right? So suppose this is my plane, complex plane. Now I write it this way. So this is the circle of radius r, and this is the angle theta. So this point, this is my complex number, so this is my complex number Z. Right? Now let's learn a very important formula, Euler's formula. Now, Euler states that Euler states that E for I theta, that can be written as cos theta plus I sin theta. Okay, we'll learn how this is very important later on. For right now, just know that Euler's formula states that E for I theta is equal to cos theta plus I sin theta. Okay. Now let's look at a unimodular complex number. Okay. Unimodular, the name itself suggests the modulus or the absolute value of the complex number is 1. Right? So this is how the modulus is written. This is equal to 1. So actually if you remember, the modulus is given by root of a squared plus b squared, where a and b were the real and imaginary parts respectively. So now let's look at the complex number in the Euler's formula. So cos square theta plus sin square theta is equal to 1, and square root of that is also equal to 1. So any unimodular complex number can actually be denoted by cos theta plus I sin theta, which can further be written as e power I theta. Right. Now complex numbers are just like our normal numbers. We can perform all the algebraic operations like addition, subtraction, multiplication, division. All of them are possible. Now for all of them, for the first three, addition, subtraction, multiplication, it's fairly simple. So if you have Z1 equal to A plus IB, Z2 equal to C plus ID, for addition it will just be the real parts will add up, the imaginary parts will add. This is for addition. For subtraction, this is Z1 plus Z2. Z1 minus Z2 will be A minus C plus B minus D. Similarly, Z1 Z2 will be A plus IB into C plus ID. We will have to just expand the brackets here. So you see that A into C, that is actually a real part, no imaginary component. The next is I into BC, has some imaginary component. A into ID, that is I into AD. And last is IB into ID, which is I square. Now we know that I is square root of minus 1, or I square is minus 1, right? So this will be actually AC minus BD plus I times BC plus AD, right? So this is the real part, this is the imaginary part. This is for multiplication. But in case of division, it is slightly complicated. We have this as C plus ID, right? Now we have to multiply this by something known as its conjugate. I'll be teaching that just in 2 minutes. So C minus ID, I multiply this by C minus ID, right? Why do I do that? Now when we expand the denominator, we will understand. We will get something. We will get just this much, C square plus D square, which is the actually square of modulus of Z2, and hence we have in the denominator we just have a real number, right? And now the upper part can be easily multiplied using the formula above, or just expanding the bracket. Right? So this is the only thing. This is the only exception in division. You just have to multiply this by its conjugate. So what exactly is a conjugate? Conjugate, right? So my complex number is denoted by Z, which is A plus IB. My conjugate is defined as Z bar, which is A minus IB, right? Now, what exactly does a conjugate do? A conjugate will, when added to the number when added to its conjugate, will just give a real number. That is how a conjugate is defined. So, Z plus Z bar will give you A plus IB plus A minus IB, or 2A. So, there is no imaginary part, right? So, this is the purpose of a conjugate. This is how it is actually defined. Okay. Now, because the real part and the imaginary parts have the same value, except that the imaginary part has a different sign in the conjugate. So we have very interesting properties. These are some of the most important properties here. Okay. So suppose Z bar is the conjugate of Z. I take again the conjugate of this, of this complex number. They should give me back Z, right? See, I have A minus IB. In the simplest form, I can always write it as A minus IB, Z bar, right? So, if I again take the conjugate, instead of minus B, I'll have minus of minus b, which is plus b, which gives me back my original complex number. Now mod of z is equal to mod of z bar. Z plus z bar is equal to 2 times a, but a is nothing but the real part of z, right? So that is actually written, this is the notation, this is the way it is written. Re stands for the real part of z. Similarly, z minus z bar gives me 2 times, imagine 2 into I times imaginary part of z, right? And then z into z bar is equal to, now let's see, a plus ib and a minus ib. So this is equal to actually a square plus b square, which is equal to the mod z square, which is also equal to mod of z bar square. Now this is the property being used in the previous one, right? C plus id is multiplied with its conjugate c minus id, so that you just have a real number in the denominator, right? Now if there are two complex numbers z1 and z2, the mod of z1 minus z2, this denotes distance. Okay, so graphically, suppose this is z1. Okay. Sorry. Right, and suppose this is z2. So z1 minus z2 is actually this. By vectors we know that this is z1 minus z2. This actually denotes the direction as well. But if we just take the magnitude, that will tell us the distance between the points z1, the points having these two vectors, right? Okay, so this denotes the distance between z1 and z2. Now let us look at probably the most important formula or theorem in complex numbers. This is called the De Moivre's theorem. Okay. Now De Moivre's theorem states that e power I n theta is equal to cos n theta plus I sin n theta. Right. So Euler's formula told us that e power I theta is equal to cos theta plus I sin theta. But De Moivre's theorem actually generalizes that and says that e power I n theta is equal to cos n theta plus I sin n theta. Right? Do note that n theta is the argument now, it's not just theta. Okay. Now this is actually used in a lot of cases, one of the most important being to find out the cube roots of unity. Right? Okay, so let us say z cube is equal to 1, right? Now, to find out the cube roots of unity, I will write this way: z is equal to 1, cube root of 1. Fine, but what is 1? 1 is actually cos of, now let me write this in polar form. So this will be actually equal to cos 0 plus I sin 0, right? But 0 is actually our, I am just taking the principal value. If we take all the values, I should write this as 2n pi. Hence, z is nothing but cos 2n pi plus I sin 2n pi for 1 by 3. Right? So that gives me z is cos 2n pi by 3 plus I sin 2n pi by 3. Do you see how you get by 3 here? Now look at cos 2n pi plus I sin 2n pi. If this is this is now written using Euler's formula as e power I 2n pi into 1 by 3 actually gives us e power e power I 2n pi into 1 by 3, right, which is e power I 2n pi by 3. Hence, we get z is equal to cos 2n pi by 3 plus I sin 2n pi by 3. Now, when we put the values of n, which is a natural number, we get it's actually a whole number. N is actually an integer. Let's just put the whole numbers here, right? So if I put 0, I get 1 cos of 0 plus I sin 0, which is 1. If I put n is equal to 1, I get cos 2 pi by 3 plus I sin 2 pi by 3. Let's put n equal to 2, get cos 4 pi by 3 plus I sin 4 pi by 3. Now if I put 3, I get cos 2 pi plus I sin 2 pi, which is nothing but 1 again. If I put n equal to 4, I get back the second root here, right? So these are actually repetitive, and these are the 3 different roots. These are called the cube roots of unity, and these are actually written, they are usually written as 1 omega and omega squared. So the second root cos 2 pi by 3 plus I sin 2 pi by 3 is usually written as omega, and it's easy to see that when that is squared, suppose omega is equal to cos 2 pi by 3 plus I sin 2 pi by 3, again using de Moivre's theorem, we can find that the next one is nothing but omega squared, right? Okay. Now, let us find the sum of these roots. So 1 plus omega squared. Now, you can very explicitly find it out, but having learned from the lecture on quadratic equations and expressions, we see that z cube minus 1 equal to 0. This is our polynomial expression. Hence, the sum of roots here should be the negative coefficient, the ratio of negative coefficient of z square to that of z cube, right? Coefficient of z cube, but there is no z square term here. Hence, the sum is 0. Okay, so this is a very important result. And now the product of the roots 1 into omega squared, which is omega cube. Again, we can use those relations to find out this, but it's better to look at it this way. Now, omega is actually a cube root of unity, right? So hence, omega cube should give us unity back, right? So omega cube is equal to 1. Now, since I told that these are actually of the form of cos of 2n pi by 3 plus I sin 2n pi by 3, hence they are repetitive. Hence, omega power 4 gives us omega power 5 gives us omega squared, omega 6 gives us back 1, and similarly omega 7 gives us omega 4, which is omega, right? So, these actually go back this way, 1 omega squared, then again 1 omega squared, 1 omega squared, right? There are a lot of questions asked on these specific properties of the cube roots of unity. Okay. Now, a very important tricky concept. So, what exactly is the logarithm of a complex number? I hope you all know what logarithm actually is. So, now logarithm is actually defined only for real numbers, right? Not only for positive numbers, not even negative numbers are not even 0. But how do we exactly define logarithm for a complex number then? Right. Suppose my z is x plus iy, right? Instead of a plus ib, I will write this time x plus iy, and I want to find its logarithm, right? Now, if it is not specified, then the base of the logarithm will always be e, the Euler number. So log e of z, or it can be written as ln of x plus iy. Now let this be equal to a plus ib, right? Now, it's very simple to actually find out what A and B are. So x plus iy can now be written as e power a plus ib, right? Which is further e power a into e power ib, which can be written as cos of b plus I sin b, right? Now we know that a complex number, on the left hand side we have a complex number x plus iy, on the right hand side we have e power a times cos b plus I sin b. Now two complex numbers are equal if and only if their real parts and the corresponding imaginary parts, both of them are individually equal, right? Hence, solving these actually, we get this formula for the logarithm of a complex number. So a is equal to half of ln x squared plus y squared, and b is equal to tan inverse of y by x. To write a specific value of b, we can add a 2k pi or 2n pi to this here. Removing this will give us the principal value, or putting n equal to 0 will give us the principal value. Otherwise, this is how you write the logarithm of a complex number. So ln x plus iy is nothing but the real part is half time ln of x squared plus y squared. The imaginary part is tan inverse of y by x plus 2n pi, right? Okay. Now let's look at the rotation of a complex number. Okay. Suppose there are three complex numbers z1, z2 and z3, right? Now what I'll do is I'll shift all of them I'll shift z1 to the origin of our complex plane. Fine. Now this is z1, z2 minus z1. So I write it this way, and this is z1 minus z3. Right? These may not be exactly equal, but just understanding the point is more important. So if this is my origin, this will be z3 minus z1, it is z2 minus z1, right? So rotation actually is nothing but the concept arrived from this. Suppose my z2 minus z1 is actually rotated by this angle alpha with the modulus of the new rotated complex number may be same, may not be same. So how exactly can I represent z3 minus z1 in terms of z2 minus z1? So this is actually a very simple formula, which again is derived very easily. The result actually is more important. Okay, so this is the formula z3 minus z1 divided by z2 minus z1. Mind you, these are the complex numbers. This is just the classic case of division we read few slides back. But this can be just written as the mod of z3 minus z1 by mod of z2 minus z1 into e power I alpha. Okay, so e power I alpha is, this is the angle alpha, the angle of rotation, and e power I alpha is nothing but using the Euler formula cos alpha plus I sin alpha. Okay. Now let us look at what a line is, how we can represent a line, the general equation of a line. Right. So ZA bar plus Z bar A plus B equal to 0. This represents a line. Now B here is actually a real number, whereas Z and A obviously are both complex numbers. Now for this, to find the slope of this line, actually it's pretty simple. What I'm supposed to do is express both Z and A, express both of them in terms of their standard notations. So let Z be equal to x plus iy, and similarly Z bar x minus iy. And expanding this further and further, you will see that the slope is actually minus real part of Z by my bad here. The real part of A by imaginary part of A. So this is the slope of this line, minus real part of A by imaginary part of A. Now similarly, a circle. How can we represent a circle? Circle can be represented as ZZ bar plus Z bar A plus ZA bar plus B equal to 0. Now you see that to this line we just add one term ZZ bar, okay, and again B is a real number. Now for this circle, the center is located at minus A. Now again, A is a complex number, right? So the center is not a real number. Center can be anything, obviously. Center can have a real part and an imaginary part. So center also is actually a complex number. So this actually justified. Center is minus A. And radius. Suppose the radius is R, obviously a complex number. This is denoted by A bar minus B. A bar or mod of A square minus B. Okay, so this is the radius of the circle. Right. So that concludes all the important properties and formulae of this chapter. There are a lot more, but they will be more particular, and they can easily be if the basics are clear and if these formulae are well remembered and can be easily, if these can be easily if recollected in the exam, then further all different particular formulae can be derived. Thank you.